volume recording. The reason why we start with population is I think there's a reasonable assertion and argument to be made that a lot of what we see in terms of environmental degradation, whether that is climate change or soil degradation, whatever topic you want to pick, is the result that we have been a remarkably successful species, right? And that the number of people on this planet is overwhelming. There's too many, and that it's not just about that there's so many people on the planet, it's their levels of consumption. And that's an important theme that we'll see in this course time and time again, that the United States, without in any way trying to point fingers, this is one of these facts. It is what it is. The United States is a consumptive country, right, on many, many levels. And there is an enormous disparity in the world. It's changing, but there is still an enormous disparity in the world in terms of consumption and the environmental impacts of that consumption, right? So a lot of people would say if we had 2 billion people on the planet, we wouldn't be in this mess. But it's more complicated than that. And there's a lot of questions that come out of that. And so that's why I dedicate two lectures here to population. The first part deals with the dynamics of population. And the second part deals with global demographics, right? So populations around the world and so on. So that's where we're headed. Okay. So before you all get your calculators out, I was born on the 5th of November, 1964. I'm 56 and a bit. And I plugged my birth date into an online calculator, if you like. And apparently when I popped out, I was the 3,319,727,000th person on the planet. Well, okay, that's an estimate based on population growth statistics. Point is, when I came along, there were 3.3 billion people on the planet. Now, I know some of you may be a little younger than me, okay, and some of you may be 18, 17, 19, some of you may be older than that. Let's say the average age in this class is 20. I don't think that's an unreasonable number to pick. And if each of you are on average 20 years old and you came around on my birthday, thereabouts, you would have been about the 6.3 billionth person on the planet, right? So that's quite extraordinary, I think, that I'm in there at about 3.3 and you come along and you're not quite double, but pretty close to a doubling in the population, right? Over a human lifetime, and considerably shorter than a human lifetime, a generation or two, okay? So to me, that is a very important launching point for looking at what that means, the implications of that, right? The ramifications of a planet that is ultimately finite in terms of its resources, not all of them, but most of our resources that we consume. And how do we manage that, right? That's one of the open-ended questions I framed last time. How do we manage the commons? So that's the context, right? That's the framing of why we look at population and the impact of population growth. Okay, so just a couple of very important demographic indices here, and I'll talk a little bit about how I ask these types of questions in the exams, but let's get to the indices for a start. So we look at population growth, right? Sorry, let me just stop and see there's a question. Okay, so that's an interesting question. So Nyla asked, what caused such an exponential growth in population in recent years? Hang on to that, right? We'll get to that, okay? And what is the theory behind the cause of the increase? Okay, we're getting to that. Good stuff, right? There's a lot of things that play out. Okay, so hang in there. We're going to get to that. One, how do populations grow? Well, it's fairly simple, right? It's the number of people born. So we have something called the birth rate, okay, the number of people born, and we express that as a rate. So this is the number of births, B, per 1,000 per year, right? How many births there are in the world per 1,000 per year. So why per 1,000? Well, if you're going to compare birth rates around the world, right, it doesn't really make sense to look at the birth rate in a large population like China versus a birth rate in a very small country like the island of Mauritius, right? China obviously has a very large population and probably has a large number of births. Indeed, they do. So we try and normalize the data to make sure we're comparing apples and apples. So what is the rate of births per 1,000, right? So that's the first demographic statistic, if you like, the birth rate. And as you would imagine, the other one is the death rate, right? The number of deaths per 1,000, okay? One minus the other is the growth rate, right? Or the rate of natural increase. So that's the first important one over here. So that's the RNI, the rate of natural increase, or R, the growth rate, okay? And the birth rate minus the death rate gives you the rate of natural increase. So let's say we've got a population of 10,000 people, and there's 2,000 births in that 10,000 people in a year, or 200 per 1,000, and there's 1,000 births, 1,000 deaths in that population in a year, or 100 per 1,000, then the birth rate is 0.2, and the death rate is 0.1, right? That's 200 divided by 1,000, or you could, of course, just simply take the total population, the total birth rate of 2,000 divided by 10,000. It doesn't matter. My point here, everybody, is that in this instance, in this simple example, the birth rate is 0.2 and the death rate is 0.1, right? 0.1 as a decimal is the same as saying 10%. So the rate of natural increase, or the birth rate of a population that has a birth rate of 0.2 and a death rate of 0.1 is 10%. Everybody needs to be happy with that. Okay, that's just a simple calculation, right? A 10% birth rate. Does that seem, if I was to ask you, do you think that's a high birth rate or a low birth rate or something in the middle? What do you think 10% sounds like as a natural rate of increase? What do you think? High? Low? High. Yeah. High. So Taylor, why high?
Because I mean, if you take the population and you take 10% of that, if you have a high population, 10% of a population increasing every single year, I mean, that's an exponential growth overall.
Right. Sorry, can you guys just give me 1 second here? There's something that I need to be made aware of. Let me just hang on a second here. Okay, cool. Sorry about that. So yeah, Taylor, thanks for that. The growth rate of 10%. I mean, you've got a population of 1,000, right? And it's 10%. You're growing at 100 every year, and then another 100 and another 100, and that growth rate starts becoming enormous. Okay, so 10% is huge. Okay, as a rate of natural increase. Now, another way to look at this, okay, is to calculate what we call the doubling time, right? The doubling time. So this is a very important demographic statistic, and the doubling time, I've written it here as T little d. The doubling time is the time it takes, literally, for a population to double, right? And there's a very important assumption here, everybody, and that assumption is assuming a constant rate of increase, right? A constant rate of R. And you calculate the doubling time by taking 0.7 and dividing it by R if you're expressing the R as a decimal. So in the previous example, right, the growth rate was 0.1. Okay, so 0.7 divided by 0.1 is what? That's 7. That's 7 years. It will take 7 years for the population to double, right? The doubling time can also be expressed as a full percentage. So if it's the full percentage, it's 70 divided by the rate of natural increase. And here you would divide it by a full 10%. That would still give you 7 years. So I want to make sure you're all happy with what the doubling time is. So Taylor's absolutely right. That's a very high rate of natural increase, right? 70 divided by 10 means that population will double in 7 years. Does that make sense, everybody? Everybody good with that? My phone is exploding. Let me turn that off. Okay, All right. So that's the first baseline of looking at a population. Birth rate, the death rate, and we could express it as a doubling time. Now, looking at how a real population grows, right, you have to then take into account immigration and emigration, right? People like me that came to this country and people who leave, the immigrants with an E, people who leave a population. So again, that's fairly straightforward, right? We just look at the rate at which people are arriving and the rate at which people are leaving, okay? So if you are to then calculate the actual growth rate of a population, okay? Let's say we're back at a population of 10,000 here. I know this looks like some complex math, but it's not, it's very simple. So let's say we've got a population of 10,000, right? And we've got a birth rate of 1,000 per 10,000, a death rate of 500 per 10,000, an immigration rate of 10, and an emigration rate, people are leaving at the rate of 100, right? So how do you calculate the growth rate of that population and the doubling time? Well, the birth rate divided by the population, 1,000 divided by 10,000 gives you 0.1, right? So that is birth rates minus death rates. And then we've got to add to that the immigration rate and the emigration rate, right? So the birth rate is 0.1. The death rate is 500 divided by 10,000, which gives you 0.05. The immigration rate is 10 divided by 10,000, which gives you 0.001. And the people leaving is 10 per 10,000, which gives you 0.01. You subtract those two brackets and add them together, you get a growth rate of 0.041 or 4.1%. And then if you take the doubling time, it is 70 divided by 4.1 or 0.7 divided by 0.041. We get a doubling time of 17, excuse me, 17 years. So in an exam, everybody, I'm not going to make, I'm not going to give you complex calculations, but I would almost certainly give you a table with some data and say, hey, folks, here's a population, here's the birth rate, the death rate, the immigrants, and then give you some choices. What do you think the rate of natural increase is? What do you think the doubling time is in this particular population? So let me stop there and make sure everybody is on the same page. Any questions on there? All good. Pretty straightforward, right? Now, immigration is, to some people, a controversial issue, and I don't necessarily want to get into any controversy here on immigration, other than to say immigration in many countries is enormously important in terms of the overall growth of that population, right? So when you look at the United States, for example, and I've just tried to summarize it in this diagram here, this shows, I think it's a really interesting set of data. So it shows the number of immigrants in terms of the percentage of the US population that were foreign born and how that has changed over time, right? So you can see here back in the 1970s, early 1970s, something like 5% of the US population was foreign born. This is as of 2019, okay? Almost 14% of the US population is foreign born, and I'm one of them, right? I'm an American citizen, but I was of course born in South Africa. And if you just look at these boxes that I've tried to summarize down at the bottom here, okay, the summary boxes are, if you just look at a 5-year period between 2014 and 2018 in the US, right, the natural rate of increase was about 6.3 million people. That's the natural birth rate minus the death rate over that period, right? But you can see in that 5-year period, we added another 2.4 million people, right, to the population of the United States. In other words, fully a 30% of the increase in the US population is as a result of immigration. So let me stop there and see if there are any comments or thoughts or questions. And we're going to examine this in a broader context when we get to Tuesday and we're looking at global countries. Any thoughts or comments?
I have a question.
Yes, cool.
For the 2.41 million, it says immigration, both legal and illegal. How are they getting accurate counts of illegal immigrants?
I knew that would come up. Yeah, that's a really good question. So that's legal immigration and an estimate, right? It's an estimate based on on a couple of sort of demographic models, looking at sort of, what we think that has been over a long period of time. It's a really great question. So is it 2.41 or is it 2.43? Not quite sure. Good observation. Yeah. Okay. All right. So moving on. So the rate of the population growth rate, right, is key in terms of how populations grow over time. And I just want to make sure that you appreciate, what we mean by that. So look at this, for example. This is the population growth rate, okay, and the years it takes to double that population, right? So if you're down here, okay, and you've got a growth rate of 10%, right? Or sorry, if you're up here and you've got a growth rate of 10%, and you come down to this axis, that population will double in 7 years, right? Okay, and so I've just taken growth rates and calculated doubling times and plotted them and put on a couple of interesting countries here. And again, we're going to get into the details of this as we get a little lower down. So in 2019, the US growth rate was 0.59%, right? In other words, we would be doubling in about 119 years. Currently, the US population is, does anybody know, right off the top of your bat?
300 million.
Yeah, good stab, 328, yep, something like that. Good stuff. So we should be barreling towards about 660 million people in 120 years. Well, not so fast, right? We can't just do that. We can't just project out, because remember, the doubling time assumes what? It assumes a constant rate of natural increase. And we know, as we'll see on Tuesday, that the rate of natural increase is decreasing over time, right? That rate's going down. But the point remains the same. Look at a growth rate here. A lot of people would look at this and go, the growth rate of 2.57, that doesn't sound very big. We could handle that. Well, a growth rate of 2.57 gives you a doubling time of 27 years. Okay, that's extraordinary if you have to start thinking about resources and things like that, right? So I just wanted to I thought that was perhaps an interesting way to plot the data. Okay. Another important concept, let me just sort of lay the groundwork here for as we move forward, right, is different types of growth, exponential growth versus linear growth, okay? And so I write a little bit about this example. You can use different examples about the famous fable about someone who was offered the choice of 1 grain of rice, and then the next day getting 2 grains of rice, and then the next day doubling it to 4 grains of rice, and the next day doubling it to 8 grains of rice. Would you rather have that, right, over a period of, say, 64 years, or would you rather get, 10 grains and then 20 grains and then 30 grains and then 40 grains? In other words, increase the number of grains of rice by 10 every day. And of course, you can see the image here makes the point, right? By the time you get to square number 20 on this chessboard, you've got millions and millions and millions of grains of rice, right? So that's exponential growth versus linear growth. And here's my attempt to just sort of draw this and in a simple way and to simplify it. So this shows population in thousands on the y-axis and time here on the x-axis, right? So 2 different types of growth here that are important in terms of the environment and things like resources. One is linear growth. So this is linear growth where you're just increasing the y unit by the same amount every time, right? So this may be, 300 people, and then you're going to 400, then 500, then 600, 700, 800, and so on, right? You're adding the same amount every time, as opposed to exponential growth, right? Exponential growth, which is the example of the rice on the chessboard, right? Where it's going from 1 to 2 to 4 to 8 to 16 to 32 to 64 to 200 and so on, right? So exponential growth. And a very important essay was written in the late 1700s by someone called Thomas Malthus. You may or may not know this person or recognize this name. And it was an essay on population growth. And the take-home message from this essay on population growth, everybody, was that populations grow like that, whether they're human populations or organismal populations, and things like resources grow like that, right? And the point of this whole discourse and essay was that we would at some point run out of resources. Okay, this was back in the mid 1700s, 1770s, I believe, something like that, right? And that's an open-ended question that we're going to pick apart and explore for the rest of this course. Where are we, if indeed this is true, right? If we can only increase something like, let's say the green line here is food. If we can only increase food at a linear rate, and populations are doing that, have we gone past this point? Are we still way down here where we've got plenty of food to feed people? Or are we somewhere up here where we have already outstripped our supply, right? Does that make sense? So just be aware of linear growth versus exponential growth. Okay. So this is very important, okay? How do populations then actually grow? And do they grow at this continually rapidly expanding exponential rate? Well, the answer is no, they don't. And here is why, okay? And we can do this for, let's say, you know, bacteria in a petri dish, right? If you've got population in thousands here, and you start off with 2 becomes 4, becomes 8, becomes 16, and so on, your population will grow slowly at first, and then will begin to multiply, right? It goes through 2,000, 4,000, 16,000, 32,000, and so on, right? If your population is growing along an exponential curve like this, it's growing along what we call a J curve, right? So there it is, a J curve. So a particular organism has a maximum rate at which they can reproduce, right? We call that rate, everybody, the biotic potential, right? What is the maximum rate at which a group of organisms can reproduce? The biotic potential, okay? And we see that if you think about a closed system, and you're looking at bacteria growing in a closed system, like a petri dish, right? They expand and multiply and exponentially grow at their biotic potential. Then eventually they reach a peak, and then they do what? Well, then they begin to die off, and they die out, right? As they die out of resources, air, and space, and so on. So the question here is, how do human populations grow, right? And where are we along this population's growth? The reality is, organismal growth follows what we call the S curve, right? Which I've circled down here. The S curve is a curve where populations grow initially quickly, but then immediately begin to slow down and taper off because of this shaded area here. And the shaded area here is what we call environmental resistance, right? And the environmental resistance, everyone, are things like low food supply, decreasing oxygen, predation, space, disease, and so on, right? In other words, a particular environment should set down a set of controlling factors that means a population should begin to slow down and reach some kind of equilibrium. And this is the most important term from the entire lecture today. Carrying capacity, okay? What is the carrying capacity of this particular environment? And I've written this term very specifically here, theoretical carrying capacity, right? Why is it theoretical? Well, if we were to take, when my son was very young, he wanted a saltwater aquarium, right? That movie Finding Nemo cost me a fortune. Nemo comes out and everybody wants a saltwater aquarium. Everybody's got to get a Nemo and a Dory. And so off we go and we get, you know, a small saltwater aquarium, and we put the anemone in there, and the fish go in there. That aquarium has a carrying capacity, right? A carrying capacity. I see your question, Dylan. I'll come back to it in a second. That carrying capacity for a small closed system is what it is, right? We can put only a certain number of fish and coral in there, and eventually it will begin to die out because of environmental resistance, like space and competition for resources, right? You can quantify the carrying capacity of a small system like a saltwater aquarium, but what about the planet, right? This here is the big open-ended question for this class. Where are we on this curve? So Dylan, if we come back just to answer your question, the question was, can you explain the S curve again? The S-curve is the actual growth curve that populations follow because of a cluster of factors that we collectively call environmental resistance. Does that make sense? Did that help? Right? These things that slow down and limit the population of a particular ecosystem, or in our case, the planet. All good? So for the planet and for this class, this is going to be the million-dollar question, right? What is the carrying capacity of our planet, right? So the question here is, yes, so the S-curve is the realistic model while the J-curve is unrealistic. I think that's true for the planet, right? So the theoretical carrying capacity is the upper limit of how many people can our planet support, right? Because think of it this way, everybody. As you'll see, the human population growth curve, here I come along, let's say this is where we currently are. So I'm born here, 3.3 billion, and that curve does that. And you folks are born here in and around the 6.4 billion. And let's say we are currently at this point. Current population of the planet is 7.8, right? Something like that, billion, okay? Let's say we are here at this point. My question is, are we there and the carrying capacity is here? Or is the carrying capacity here? Or is the planetary carrying capacity here, right? Have we already gone through the carrying capacity? In which case, some sort of corrective action would need to happen. So let me stop there and see if there are any thoughts or comments and whether that makes sense, right? Keegan, does that make sense in terms of the theoretical carrying capacity? Thumbs up, good. Okay, awesome. Okay. All right, here's an interesting question, Holly. Do you think COVID is one of the environmental resistance? That's a really interesting question. There's a couple of questions about COVID. Gosh, I don't know. I'm not an epidemiologist, but certainly there are things like viruses and plagues, and maybe those are nature's way of saying, hey, everybody, we need to pay attention here, right? Now, is COVID on the scale that it will cause the population to go from 7.8, back to 4? Well, of course, there's the whole thing like modern medicine and how that all plays out, right? But certainly, I would put it as part of environmental resistance. Although I wouldn't argue that we need more viruses to control population. I think ethically that's tricky. Right? Let me just take a double check here on the question from Colin. Won't the population jump over the theoretical carrying capacity and face mass famine? Or does it depend on the type of species? So that's a really good question, right? It does. It depends on not just the type of species, but it depends on the scale of the ecosystem, right? So yeah, there is an upper carrying capacity beyond which you can't put more people onto a vehicle, right? Or you can't put more people into the planet. But we do know that species do experience what we call population overshoot, right? So what is population overshoot? Population overshoot is when a population actually goes through its carrying capacity and shoots beyond that and then experiences what we call dieback, okay? So whether that is Colin, mass famine or an outbreak of something, okay? A resource runs out, okay, you massively run out of food and you experience a population dieback, and then maybe that population can recover, at least theoretically. That particular population, that species, should come into some sort of balance or equilibrium with its carrying capacity, right? So the short example that I use, and you can just read this on your own in the book, is what happened on Isle Royale National Park. So Isle Royale National Park is an interesting one. It's a very well-studied national park. So here's Lake Superior, right? And Isle Royale National Park is here in Lake Superior. Here's just a map of the park, FYI. And the reason why it's been so well studied is the relationship that has been observed between wolves and moose on Isle Royale National Park, right? So this is the relationship between wolves and moose. So here on the y-axis on the left is the number of wolves, and so that's this brownish one. And here's the number of moose, okay? And it's how those two species, so wolves prey on moose, that's their major prey, right? So when you look at the number of moose, okay, where the number of moose start increasing here in this period was a disease outbreak in the wolves, okay? And then when the wolf populations recover, the moose populations go down, right? And when the wolves populations go down, the moose populations go up. The point here, everybody, is that the populations should be somewhere, you know, in a boundary like, well, that. And at some point they experience overshoot and die back, right? How does that play out in human populations, I guess, is the unknown question. There's no answer to that necessarily, but that's one of the questions that we really are going to try and address as we move through this course. Okay, a couple of quick questions here. Can you explain biotic potential? Biotic potential, yes, Queen, it's the maximum rate at which a population can reproduce, okay? Okay, a question here, what are the qualifications we go off to justify if we have reached the carrying capacity? So Caden, that's an excellent question, right? What are the qualifications? How do we define that? If I was to turn the question on you, is there something that jumps to mind that you can say, yep, if we've crossed this, then we're through the carrying capacity, or is it not that simple, do you think? I don't know if you can hear me, but
on a basic level, just like how much food like we can offer for people to eat to sustain life.
Right. Okay. So that's a good one. We generally need food to survive. Okay. So let me pose this, because when on Tuesday when we look at global populations and we talk about food, do you think there is enough food currently on the planet to feed the world?
Yes.
Yes.
Yeah. Right. Yes, I think is the consensus that we currently have enough food, right, on the planet to feed the world. So then why do 1.5 billion people go to bed hungry at night?
I think this is the problem for why some people can't get food and some people do have food.
Sorry, say that at Genera again. I missed your first part.
Distribution is mostly the problem as to why some populations have more food than others.
Unequal distribution, right? Absolutely, right? Waste, enormous. How much food we waste here in the United States is quite extraordinary, right? So is there enough food to feed the current population? Well, yes, there is, and we should be in good shape if we can get our distribution channels correct. But what happens when another 2 billion come along, right? And that's something we're going to talk about on Tuesday. Will there still be enough food, or will now we have 3 billion people that go to bed, you know, hungry at night? Okay, so enormously problematic. So yeah, access to food, distribution to food, corruption in the distribution networks, and so on and so on, right? I'm just scrolling through the comments here, some good comments here. And some regions, yeah, that's a good question. No, in some parts have an abundance of food, right? And some do not, okay? And then there's also the issue of environmental justice or injustice. When you look at who has access to food, right? Who has access to healthy, you know, nutritious food, okay? I'm in a very fortunate position that I tend to not think about whether I can get enough calories in a particular day, okay? Kevin, we're going to address that on Tuesday. Why does and did China have a child birth limit? Good question. Hold that thought until Tuesday, because we're going to come and put this in the context of global demographics. Okay. So, so that's really it, I think, for the day. We may end just a little early, which I think is absolutely fine. Again, as always, I'll hang around. But my point here was for you to just appreciate that there are some mechanics to population growth, and then there are some very big, broad questions as to how we apply those mechanics to a global population, both as a whole, 7.8 billion, and then regionally in smaller and smaller regions, you know, of the world. Does it matter that we're going to have very likely another 2.5 billion people come along or not? So that's me for the day. A little early release time. You're welcome to disappear. Please don't forget your tweets. And as always, I'm going to hang around to see if there are any comments, thoughts, or questions. So be safe. Have a great weekend, everybody.
Thank you.
You bet.
Thank you.
Yep.
I have a